Have you ever wondered what physics is being used that enables an airplane to fly? What it all comes down to is the use of the properties of Bernoulli's principle. By properly using Bernoulli's principle, that enables a 250-foot long, 212-foot wide, 776,000-pound airplane that is carrying 400 passengers to fly 6 miles in the air to a destination halfway across the world.
Depicted earlier, and with the airplanes taking off and landing, Bernoulli principle was demonstrated. The reason why that works the way it works is the air, as it hits the wing, or this is when the plane is landed and stationary, and as the plane's taking off, if this is the wing, it's going to tip to be at a greater angle. And so your air, as it's coming across the top of the wing, relative to the wing itself, is going to be going at a higher velocity, which creates so you'll have your wind speed, your air coming in, and when the wing is flat, the air will move around the wing easily without causing any sort of lift. But then as you have the wing a lot more tilted, it'll the wind has to travel on the bottom. It won't have to travel as far as it does at the top, and so this airspeed, the velocity increases quite a bit, which will create a little bit of eddies and turbulence behind you, but also create a low pressure zone, which will create lift in the wing. And this happens because the wing gives the air a downward force according to Newton's third law, and the wing experiences the opposite effect, which will create lift. As noted earlier when it was landing, when the wing comes back down, it doesn't return just to this state. It has little wings, it has little things that come up and down that essentially are causing the wing to theoretically the wing is going to just go flat, because then there's going to be too much. The wind is going to hit this, and it's going to be a buffer, and rather than creating a lift like before, it's going to increase the drag to a high enough force where it'll stop the airplane.
An example of Bernoulli's equation that can be done at home can be done with the use of a few balloons and some string. What you do is you blow the balloons up, then put them onto a string, and then tie the strings up to a ruler so that when the balloons are free hanging, they're about 5 inches apart from each other. Then, by blowing quick air between the balloons, it should cause the balloons to pull together, like so. The reason that occurred is because of the Bernoulli principle of the high-speed air between the two balloons causing low pressure between the balloons, which makes the static air push the balloons together, making the balloons appear to stick together due to the high air between it. Bernoulli's principle can be observed at home by the use of a ping pong ball and a string. What you do is hook a string up to the ping pong ball, and you set it next to the faucet of water, or a faucet, and you swing the ball like that. Once you turn the faucet on, the faucet will suck into the ball and hold the ball at an angle position. The string can't be seen, but it's actually sitting at an angle there, and it should have pulled away, but due to the force of the water, it's holding the ball off to the side. The reason that occurs is because the fast-moving water flowing alongside the ball is creating low pressure on this side, which then when the ball gets sucked into there, the low pressure holds the ball at an angle. This can be done at home.
Alright, today we're going to show you a quick, easy example of how to use the Bernoulli equation. It's going to be a tank with the fluid water inside of it. So the tank is going to be here. There's going to be a little spout at the bottom, towards the bottom. It's going to be subject to the atmosphere. So this is H2O, and the fluid will be coming out right here. We're looking for the velocity. We are also given the height, which is 2.4 meters. And so we have to pick 2 points here. Our first point is going to be at the top, right there. Our second point is going to be down here, right where the water comes out. So that's point 2. this is our reference height. And so we will start by using the Bernoulli's equation, which is P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. P1 is subject to the atmosphere, so that will be PATM plus rho GH1, which is going to be 2.4 in the end, plus 1/2 rho V1 is going to be equal to 0, relatively equal to 0 because it's going to be moving so slow relative to the way that it's coming out of the spout. So we consider that equal to 0. So this whole term is going to be equal to 0. That is all equal to P2 is subject to the atmosphere at this point as well. So that's PATM plus rho GH2 is considered to be equal to 0 here. This is our reference height. We're just measuring using the pressure differences here from 1 to 2. So the height just goes from 2.4 to this 0 value. So H2 is going to be equal to 0. So that whole thing will go to 0. Plus 1/2 0. Plus 1/2 rho V2 squared. That's the term that we're trying to find. Okay. So the atmospheric pressures will cancel out as well. So we'll be left with rho GH1 is equal to 1/2 rho V2 squared. We will multiply both sides by 2, and these will cancel out. So we will be left with 2GH1 is equal to V2 squared. So we will take the square root of each side to get rid of the squared terms. V2 will be equal to the square root of 2GH1. We know gravity, we know the height is 2.4, and so V2 is going to be equal to the square root of 2 times 9.81 meters per second squared multiplied by H1, which is 2.4 meters. So V2, all that calculated, V2 will be 6.86 meters per second.